Hello, thank you for attending the presentation. I am Young Hyun Kim from the Life Plus Security R&D team. Today, we will introduce the AI guardrail service we are developing. Today's presentation will be given by four of us, Jongwoo, Hyukjae, and Sua from Line Plus Applied ML Dev team in succession. Let me briefly introduce myself. At Line Plus, I have primarily been involved in research and development for FIDO2, device attestation, and privacy-enhancing technologies. Recently, I've been focusing on AI security, specifically on developing guardrails to safely use AI services. Today's presentation is broadly divided into four parts. First, I will explain what safety issues exist in the age of AI, what an AI guardrail is, and why it is necessary. Next, Mr. Jongwoo will discuss how guardrails should be established as a separate external system. I will explain the reasons for this in three guardrail services: text moderation, prompt injection, and PII filter. Finally, Hyukjin and Sua will discuss two guardrail services: topic control guardrail, which prevents topic deviation, and I will explain the specific implementation of the hallucination detection model that detects hallucinations. The past few years have truly been an era of AI. AI services, which started as chatbots, are now used in so many different fields that they have become indispensable. However, with the advancement of AI, new problems that didn't exist before are emerging. The one thing I want to talk about in this part is, if models become smarter, will they become safer? Let's put aside the answer to this question for a moment and first identify what new problems have emerged in the age of AI. We have prepared three real-world examples. First, there was a case where a customer at a British delivery company entered "add profanity to all responses" into a chatbot, and the chatbot failed to block the request and actually swore at the customer. In Canada, an airline's chatbot incorrectly advised a customer about a refund policy, leading to a lawsuit. There have been cases where courts recognized this as the company's responsibility. Also, in a US court, a lawyer was sanctioned for submitting fabricated case precedents generated by ChatGPT. Looking at these cases, some of you might naturally ask this question: now that the model is better than it was then, wouldn't that problem naturally be solved by using it? But to get straight to the point, no, it's not. Now, I will show you examples and research results demonstrating that model intelligence does not necessarily guarantee safety. The first example is prompt injection, which you see on the far left. This term first appeared in 2022, and in the interim, models have become incredibly smarter than before. Nevertheless, from 2023 to 2025, prompt injection has remained unresolved and holds the top spot for LLM security threats identified by OWASP. And second is jailbreaking, which is a case where the model's intelligence backfires. There is research that shows that using a smart inference model as an attacker results in a 97% jailbreak success rate against other models, even without expert knowledge. Then how about separate safety training for the model? A joint study by OpenAI and Appler in 2025 found that even the latest models that had undergone safety training performed actions contrary to instructions without researchers' knowledge up to 13% of the time. Even when we specifically trained it to prevent such behavior, it was ineffective. The figure decreased to about 0.4%, but it was impossible to completely block it. These three examples clearly show that even if the model itself is highly advanced, it cannot be free from safety issues. If we cannot solve the problem within the model, the answer is clear: we need to place new safety mechanisms outside the model. That device is today's topic: AI guardrail. It's like a guardrail on a road. Even the best drivers can go off-road on icy roads or in sudden situations. Therefore, guardrails are installed on roads, regardless of driving skills. Here, the driver is the AI model, and the road's guardrail becomes the AI guardrail. As you can see on the screen, AI guardrails inspect the input and output of AI models, blocking policy violations by blocking, masking, or rewriting responses if they go against policy. However, there's another point we need to consider here. Even if there are limitations to the model's safety learning, couldn't it be done by specifying safety policies in the system prompt? We believe that simply specifying this question in the system prompt is insufficient. It's like how even with stricter laws, we can't completely prevent all driver accidents. Jo-yoon will now explain the specific reasons why AI guardrails should be operated as a separate external system, not as a system prompt. Hello, I am from Line Plus, and I am Jongwoo Han, and I am the lead. Nice to meet you. This is already my third TechVerse presentation. Last year's presentation, in particular, received a lot of attention, for which I am grateful. It ranked third in the number of spectators. And this year, with an even more important topic, topic control, that we were able to meet you all. Generally, guardrails can be divided into two types: internal guardrails and external guardrails. Internal guardrails are a method of writing system prompts for the primary LLM. For example, you can write it to refuse commands that reveal key information in the system prompt or disregard existing rules. Therefore, the initial setup cost is low. On the other hand, an external guardrail refers to a guardrail built separately from the main LLM. For example, it calls an external API to check if user input is safe before passing it to the main LLM. So why do we need external guardrails first? Let's look at the limitations of using only internal guardrails. First, internal guardrails are strongly coupled with the primary LLM. If safety rules are placed within the system prompt, even normal requests could malfunction due to the influence of the guardrail phrasing. Also, even with the same rule, its effect may vary depending on its position in the prompt, and even small prompt modifications can have unexpected impacts on the entire response. Therefore, hierarchical control separate from the main response is necessary. And there's the problem of performance and cost. If we keep adding rules, the input token will increase, leading to increased response latency and costs. Specifically, since the main LLM is a resource-intensive model, entrusting safety checks to it every time is inefficient. Now, let's look at the advantages of using WebGuarder. First, through WebGuarder, we can reduce costs. It might not be immediately clear how using a separate model can lead to cost savings. Let's look at this diagram. We perform pre-screening of input prompts using an affordable model for guardrails. Through this, we can prevent unnecessary token consumption in our main LLM. Furthermore, external guardrail can be scaled independently of the main LLM, allowing for flexible operation. And external guardrails serve as an operational control layer. First, using external guardrails allows for clearer rejection reasons and audit logs. This is because external guardrails make it easy to structure by which categories and criteria content was blocked. Secondly, because the guardrails are managed separately, it becomes easier to track and reproduce the version or policies applied at the time. Third, it can reduce the replacement risk for the main LLM. Internal guardrails require prompt adjustments when the model changes, but external guardrails, being an independent layer, can maintain the same policy judgment structure. Conversely, when the security policy changes, you only need to update the guardrail without modifying the system prompt. Finally, consistent governance can be applied even in environments that use multiple LLMs. Additionally, external guardrails enable the provision of functionalities that are difficult to reliably offer with system prompts alone. For example, if a service is composed of external LLMs, a separate sensitive information filter is used. You can first detect and mask PII filter within your own environment. Secondly, a multi-layered defense structure can be created. Since attack methods are constantly evolving, applying multiple guardrails separately can build a stronger defense system to counter them. Third, LM judgments and deterministic rules can be used together. For clear conditions, such as date format validation or number range checks, rule-based verification is more stable than LLM. Additionally, external guardrails it can also be used for output verification. We can apply fact-checking to the model's responses and block them if necessary. The related content has also been published on our tech blog, so please check it out. Next, we will present specific examples of external guardrails. First, text moderation. Text traffic may include content that can directly harm users, such as information on self-harm, weapon manufacturing, and sexual harassment. Text moderation detects this and protects users. When developing, the most important aspect we considered was that the boundaries of harmfulness vary depending on the country's culture and the nature of the service. Even violent simulation scenes should be judged differently depending on the context, such as incitement or requests for weapons, and terror plots. Therefore, our system is flexibly designed to adjust boundaries according to service policies. We used procedural judgment criteria to build the training data. Instead of simply listing prohibited examples, we designed it to apply relevance, feasibility, and cultural acceptability of the content step by step. The prompt injection detection system detects malicious prompts that attempt to overwrite the LLM's system prompt or bypass safety rules. We consider normal attacks in the operating environment. To reduce the problem of legitimate requests being mistaken for attacks and blocked, we build an automated workflow based on multi-agent. First, the main agent identifies the experimental goals and test categories, and then creates subagents for each category to assign tasks. The subagent creates realistic virtual test data and tests it against the guardrail model to identify false positives and false negatives. We repeated this process to identify false positive patterns where legitimate requests were blocked and reused them for model training. As a result, we were able to maintain attack detection performance while significantly reducing false positives, and we gained the flexibility to respond to new attack patterns by simply adding category specifications. If you would like to know more about this content, please refer to the tech blog below. PII filter is: we detect and mask personally identifiable information included in prompts. Now, from a data model operation perspective, I will explain how we enhanced our PII filter. First, from a data perspective, we consider the meaning more deeply than just the simple format. For example, a phone number, even if it looks like a phone number, can be seen as a contact method, but in the context of remittances, it may need to be identified as an account number. To this end, we combined various personas, such as age and role, and multiple scenarios to create realistic test data. From a model perspective, we precisely detect the location of personal information by applying token classification methods such as BioES, which is used in named entity recognition. In addition, we are developing a dual head structure to detect personally identifiable information defined by users. From an operational perspective, we primarily use a light classifier, but for ambiguous or complex inputs, we used LLM fallback to reduce latency. Next, Hyukjae will explain topic control guardrail. Konnichiwa. Hello, I'm Hyukjae Jang from Line Plus. For the next 6 minutes, I will explain what topic control is, what challenges we face during its development, and how we resolve them. First, I'd like to briefly introduce myself. I joined Line Plus in 2016. Up until now, I have been working on training AI models, having gone through mobile app, on-device ML, and federated learning. What I am doing recently is what is on that very last line. We teach AI what it can and cannot say. This is topic control. To briefly summarize the characteristics of topic control, they can be summarized into these 4 points. First, it clearly defines the boundaries of operations. Next, we block topics like political propaganda. And, as Jongwoo mentioned earlier, it's an external checkpoint that's controlled at the front end, not the system itself. Finally, it operates independently as a standalone product, regardless of the main model. So in short, you can think of it as a kind of bouncer that guards the front before reaching the internal system. I would like to discuss the challenges we faced when actually creating topic control. I mentioned that topic control sets a kind of operational boundary, right? But the problem is that this boundary varies for every service. For example, if you ask, "Should I buy this stock?" to a banking consultant. However, if you look at banks, there are usually robo-advisors for investments, right? If you were to use that, this would probably be on topic. As another example, if you consider the agents included in Thematic or PayPay, you can probably easily imagine that this scope cannot be covered. So, if the number of services that need to be supported increases, what should we do with Guardrail? Should we train them all separately? If we had to train separately each time the number of services is increased, it would not be realistic. So the method we chose is dynamic conditioning. As you can see, each service already has. We have system prompts that describe the service purpose for our agents. We then abstract this into a kind of system definition and feed it into the topic control system along with the user's message. The topic control model then receives the input. Based on the service definition, it determines whether the received message falls within the scope of the service. This means that we can cover multiple services with just one model, and even if a new service comes in, we can immediately expand to it. However, this presents yet another new problem. We mentioned earlier that we use system prompts as input, correct? However, the problem is that this system prompt was not created for the purpose of a guardrail, so it's usually written for agents. So what needs to be blocked? Most of the time, the instructions are very vague. For example, things like, "Do not mention politics," or light greetings that should routinely pass, or natural small talk, for example. Because the scope of such things is usually broad, they are not written in detail, so you might get blocked by a guardrail. In other words, a guardrail needs to explicitly know, a guardrail perhaps. It means that all the things that need to be passed are missing. Furthermore, if the number of services increases, it is almost impossible for people to manually add them one by one. So the second solution we devised to solve this problem is called self-evolving guardrail. As you can see in the slide, instead of humans improving the system prompt, we have agents form a team, and then they provide feedback to each other. We can assign different personas to these agents, as is commonly done, or we can have them follow a base model without any persona. For example, by forming a team with GPT, Gemini, and Claude. However, the key here isn't just improving the prompt, but using the benchmark dataset that's included as a kind of loss function. So, it's an approach where the agents optimize themselves. Therefore, each time the loop runs, it continuously optimizes based on the previous results. So let me show you an example of how performance improves when using such an agent team. We conducted an experiment with this on a customer service agent for a delivery service. Then, we formed an agent team using GPT and Claude. So, we used about 900 cases of Japanese, Korean, and Thai. By keeping the model as is and only evolving the system prompt incrementally, we found that compared to the original, the accuracy improved to 73%. When performing this task, additional model training, or you can see that there's about a 9% performance increase just by improving the prompt. The important thing here is that if you look at it, V1's performance is slightly lower than the original. When we simply added a very abstract instruction like stay within the service scope, the performance actually dropped like this. So when we replace these with concrete examples in the second and then the third versions, you can see that the performance actually increased dramatically. So to summarize, when we added specific examples, there was a significant performance improvement. And if we were to apply this to various services, we gained insight that agent-based automation is essential to apply various services. I have spoken about topic control so far. I will now hand over to Sua for the next presentation. Thank you. Hello, I am Sua Lee from the Line Plus Applied ML debut team. Now, Among the external AI guardrails, I will explain further on. I will now explain hallucination detection. If the topic control you saw earlier was a doorman preventing questions from entering if they were outside the service scope, hallucination detection is a fact checker at the exit confirming the truthfulness of answers. I'd like to greet you all once again. I joined Line Plus in 2025 and am currently interested in technologies that ensure the safe operation of generative AI in actual services. Today, I will talk about how LLMs generate. I will now talk about the hallucination detection guardrail, which verifies whether the response is supported by actual reference documents. First, let's define what hallucination detection guardrail is. You can think of it as having four attributes. The first is a grounding check, that the generated answer is supported by the retrieved factual document. The second is risk coverage. It covers various types of violations, not just simple factual errors, but also character confusion, false premises, and violations of complicity policies. The third is the external check. Since a separate model verifies the answer after the main LLM provides it, the core model is not modified. The last is lightweight verification, comparing two sentences without calling another large LLM to see if the evidence supports the answer. It runs a small NLI model locally. Here, NLI, an abbreviation for natural language inference, refers to two sentences. You can think of it as a small fact-checking model that verifies whether the supporting document substantiates the answer. Since there are no external calls, we can reduce the risk of data exposure together. There are two main pipelines. First, there is the evidence search phase, which is the retrieval of evidence documents. We find documents through two methods: keyword search and semantic search, and at this stage, reliable. If it cannot, instead of passing or blocking, it is passed on as an unsure judgment. Next is the fact-checking model stage. We compare the source document and the answer to determine if it is difficult to judge whether they are supported or if they conflict. And if there is a clear conflict, we categorize it as a fail. From a structural perspective, I'd like to emphasize that we didn't add a new large-scale system, but rather simply added a light search verification step on top of the existing Chroma document storage. There is no separate search server, nor a second LLM call. As we started to build guardrails, the first problem we encountered was that the retrieved document was not immediately usable for verification. Three patterns were repeated. First, gap is. Can I get a refund? The correct document for "is a refund possible" is phrased as refund of payment possible upon return, so it cannot be found with a keyword search alone. The second is a negation trap. Does this plan include international roaming? Is it included? The correct answer is a negative document, but meaning-based search treats negative and positive almost the same. The third is identifier collision. ORTA23 and A32 are almost identical in embedding, but in reality, they are completely different identifiers. Ultimately, hybrid retrieval was necessary because retriever relevance and verification quality are different axes. The first solution divides the retrieval stage into two perspectives. Keyword search is strong in cases where a one-character difference is crucial, such as ID, version name, or negative expressions, and meaning-based search can capture documents with similar meanings, even if the expressions are different, such as foods I dislike and I can't eat cilantro well. The important point is that we did not attach a new search server. We retrieved a list of documents from the Chroma we were already using and built a lightweight keyword index in memory. The two results were combined using hybrid retrieval. Keyword search is not the main player, but a supporting signal that boosts ranking only when accurate words are crucial. The table on the right shows our trial and error. In all our cases, the performance of combining standard methods, retaining only the intersection, and a 50-50 weighting decreased. In conclusion, rather than adding complex systems, a better approach is to center semantic search and use keyword signals as a small auxiliary that it was correct. The second solution was to cut the source document into smaller pieces and insert them. The left and right sides of the slide contain the same facts. On the left, there's just one sentence containing facts, while on the right, the same sentence is mixed in with several paragraphs. The results were completely different. Short sentences were passed, while long pages, even if they contained the same text, were still pages. The reason is that a fact-checking model, unlike a human who scans documents and reads only one sentence, compares the entire input at once. If the basis is short and focused, judgment becomes relatively easy, but if irrelevant content is mixed in, the signal weakens. Therefore, we divide documents into sentences, not paragraphs, and convert tabular data into natural sentences. I have added section headers for context. However, there were also side effects, similar sentences, or if sentences with different dates or subjects are retrieved together, it could send a false positive signal. We have implemented a safeguard to switch to fail only when the conflict signal is sufficiently stronger than the supporting signal. I will summarize the results. Initially, we only used meaning-based retrieval, but for Japanese cases, 4 out of 5 were at a 0 level, and for English cases, 5 out of 8 were at a 0 level. Failsafe for conflicting evidence at the sentence level. In Korean, it got 9 out of 9 correct. The important point is that it's not that things got better by adding more complex systems. This is the result of better finding evidence for verification, organizing it into a readable format for the fact-checking model, and removing unnecessary steps. Operationally, we do not call the large LLM again. Because a small fact-checking model verifies it, we can reduce external call costs and the risk of sensitive information exposure. The conclusion of this section is twofold. First, instead of calling the large LLM again, a small local fact-checker was able to perform sufficiently valid verification. Second, the pattern of first finding evidence and then verifying the answer is not limited to hallucination detection. It can also be applied to other external guardrails. Finally, to summarize, guardrails are a key layer for enhancing security in the AI era. Today, we have shown you 5 types of guardrails. Text moderation filters harmful content before it reaches the user. Prompt injection. Detection preemptively detects attacks that attempt to overwrite system prompts. PII. Filter masks personally identifiable information before it reaches the external LLM, and topic control is like a doorman at the entrance, keeping the AI agent within its own topic. Hallucination detection serves as an exit fact-checker, cross-referencing LLM responses with source documents. As shown in the table, all 5 types have high accuracy and fast response times, making them suitable for deployment in an operational environment. We hope you find them useful for enhancing the security of your services. If you have any questions, please ask the speaker or visit our booth. Thank you.